Algunos sueños parecen muy grandes e inalcanzables, pero son los que te impulsan a creer, a crear y a transformar. Tu imaginación y la exploración de nuevos horizontes te permitirán escribir una nueva historia y cambiar la realidad. Alcanzar tus sueños te motiva, pero aportar a una mejor sociedad te hace grande. Tu talento es el inicio de un gran futuro. Cree en ti y todo será posible. UPB.
Muy buenas tardes. Soy Luis Ángel Silva y desde la coordinación del programa de Maestría en Ingeniería e Innovación para el Desarrollo Agroindustrial, le damos la más cordial bienvenida a esta actividad académica. Esta actividad académica tendrá dos momentos. Inicialmente, se socializará el nuevo folleto con los datos relevantes de nuestro programa de maestría y en una segunda parte tendremos la conferencia a cargo de nuestro invitado internacional. Entonces, para dar comienzo a esta actividad, permítame comparto con ustedes la pantalla para presentarles los aspectos relevantes de nuestro programa de maestría. Javier, ¿me confirma si ya se está viendo? Ok. Javier, ¿me confirma si ya se está viendo la presentación? Bueno,
Presentación.
listo. ¿Sí se está visualizando, Javier?
Sí, señor.
Listo, muchísimas gracias. Bueno, nuestro nuevo folleto de maestría en Ingeniería e Innovación para el Desarrollo Agroindustrial, pues tiene los aspectos relevantes y los quería compartir antes de la charla para que los tengan presentes y puedan utilizarlos para compartirlos ya sea en su propia formación postgradual o en la de sus compañeros o familiares. Algunas generalidades del programa, decir que otorga el título de Magíster en Ingeniería e Innovación para el Desarrollo Agroindustrial, que es un programa de maestría de 3 semestres con una duración de 45 créditos en la modalidad de profundización y presencial. El horario es una vez al mes, los días jueves, viernes y sábado de 7 de la mañana a 7 de la noche. Decir que nuestro programa de maestría tiene como objetivo ofrecer a profesionales de diferentes disciplinas conocimientos en el área de la agroindustria con bases científicas y tecnológicas considerando las líneas de agroindustria digital, energías para la agroindustria e innovación de procesos agroindustriales, buscando soluciones innovadoras enmarcadas en el desarrollo sostenible, aportando al aumento de la competitividad del sector agroindustrial enfocado en los objetivos de desarrollo sostenible. Decir que nuestro programa de maestría es presencial, como lo comentaba anteriormente, y tiene la particularidad de un 27% de créditos que se pueden tomar en forma virtual, lo cual corresponde a 5 asignaturas. Un magíster en el área de innovación para el desarrollo agroindustrial se concibe como un profesional capaz de diseñar y mejorar procesos y productos en las diferentes etapas de las cadenas agroindustriales por medio del uso de herramientas metodológicas y el desarrollo de proyectos de ingeniería, aplicando nuevas tecnologías con un enfoque de desarrollo sostenible. Además, el egresado tiene la capacidad de desarrollar propuestas innovadoras desde el enfoque transdisciplinar de la ingeniería, orientadas a fortalecer los procesos en diferentes áreas de la cadena productiva agroindustrial, que además constituyen el crecimiento en términos de desarrollo de ciencia y tecnología en la región y en el país de una manera sostenible. ¿Qué perfil de egreso tendría este programa de maestría? Puede empresas públicas y privadas en sectores académicos, productivos e institucionales que tengan funciones asociadas al desarrollo del sector agroindustrial del país. Además, nuestro egresado es un profesional capaz de diseñar y o mejorar procesos y productos en diferentes etapas de la cadena agroindustrial por medio del uso de herramientas metodológicas con un enfoque de desarrollo sostenible. ¿Quiénes pueden aplicar a este programa? Está dirigido a profesionales de ingeniería agrícola, ingeniería agropecuaria, ingeniería agroindustrial, ingeniería biológica, ingeniería electrónica, ingeniería agronómica, ingeniería de sistemas, ingeniería forestal, ingeniería eléctrica, mecánica, industrial, química y ambiental y todas las áreas relacionadas con el área agroindustrial. Como comentaba inicialmente, nuestro programa tiene 3 semestres con 45 créditos. En la primera parte, en el primer semestre, pues se ve todo el background con el cual se va a trabajar en la parte de probabilidad, aprendizaje automático, fuentes de energía para la agroindustria, procesos productivos agroindustriales y seminario de investigación. En el segundo semestre se trabajará sobre la planeación y formulación y evaluación de proyectos, sistemas agroecológicos, gestión de la tecnología y la innovación, estandarización y certificación de procesos y se iniciará con el trabajo de grado 1. En el tercer semestre y último tendríamos las optativas de línea que como las relacionamos anteriormente están dadas con la agroindustria digital, la energía para la agroindustria y la innovación de procesos industriales. En la parte de agroindustria digital, el objetivo es mejorar o tener las herramientas que permitan mejorar procesos en diferentes etapas de la cadena agroindustrial por medio del uso de herramientas tecnológicas, soportado en análisis robustos de datos, aplicando nuevas tecnologías de inteligencia artificial con un enfoque de desarrollo sostenible. En el área de aplicación de energía para la agroindustria, se evalúan las problemáticas y necesidades energéticas del entorno agroindustrial para implementar soluciones que involucren energías renovables. Y finalmente, en el área de profundización en innovación de procesos agroindustriales, se plantean mejoras en procesos productivos agroindustriales orientados a innovar en el desarrollo de productos con impacto económico y social sin afectaciones del medio ambiente. También propende por analizar los procesos que conforman los sistemas de producción agroindustrial para identificar mejoras en la productividad y eficiencia en la cadena productiva. Esta maestría está soportada por 3 grupos de investigación, como es el grupo de investigación en Ingeniería mecánica, el grupo Gidetecma. También está el grupo de ingeniería electrónica, como es el grupo de control industrial, y está el grupo PROLOG, que es el grupo de ingeniería industrial. Recordarles que están abiertas nuestras inscripciones, que estamos atentos en ese proceso de admisión para solucionar alguna de las inquietudes que se presenten durante este proceso y que este proceso, pues, como comentaba inicialmente, ya se está llevando a cabo y se puede hacer a través de nuestra página web. Aquí tenemos entonces la dirección del correo electrónico de contacto maestría innovación agroindustrial.bga@upb.edu.co, quien es manejado a partir de la coordinación de la maestría y ahí está el número telefónico con el cual podemos resolver todas sus inquietudes. Entonces, este es nuestro nuevo folleto, nuestro folleto de promoción académica, que si lo desean me lo pueden pedir por el interno, luis.angel@upb.edu.co o a través del correo de la maestría y se los haré llegar con el mayor gusto. Bueno, ahora vamos nuevamente a retomar ya la parte académica de nuestra charla. Entonces voy a comentarles un poco acerca de nuestro invitado especial. Su nombre es Haoyu New y nos va a presentar la conferencia titulada Smart Big Data in Precision Agriculture, Application, Acquisition y Analytics Advanced. Esta conferencia trata sobre la aplicación del Smart Big Data a la agricultura de precisión. El Smart Big Data es una de las nuevas tendencias y de las nuevas técnicas de la industria 4.0 que utiliza los datos recolectados en un proceso agroindustrial para extraer información relevante que apoye la toma de decisiones en las diferentes etapas de las cadenas agroindustriales. El doctor Jaoyu es ingeniero mecánico y doctor de la Universidad de California, Merced, y actualmente está realizando su programa de postdoctorado en la Universidad de Cornell. Sus intereses de investigación están relacionados con el Machine Learning, el Deep Learning, el Big Data, la agricultura de precisión y la aplicación del sensado remoto a vehículos aéreos autónomos. Además de nuestro invitado Jaoyu, también está nuestro querido egresado Jairo Viola, quien es egresado de nuestra Universidad de Ingeniería Electrónica y que ha realizado su doctorado en la Universidad de California Merced. Agradecemos al doctor Jairo el contacto de Jaoyu y el apoyo brindado a las actividades académicas y de investigación que se realizan desde la Facultad de Ingeniería Eléctrica y Electrónica y del Programa de Maestría en Ingeniería para la Innovación y el Desarrollo Agroindustrial de la Universidad Pontificia Bolivariana. Muchas gracias, doctor Jairo, por su colaboración. A todos nuestros participantes, quienes nos siguen a través del canal de YouTube de la UPB, les solicito que las preguntas que puedan surgir a lo largo de la charla sean realizadas a través del chat del evento. Al final de la charla, estas preguntas serán realizadas a nuestro invitado con la ayuda del doctor Jairo. Entonces, sin más preámbulos, le damos la bienvenida al doctor Jaoyu y a su conferencia. Welcome, Jaoyu. It's a pleasure to have you always in our master program.
Yeah, thank you, Dr. Engel. Thank you so much for this great opportunity to discuss research with you and your research team. Yeah.
Okay. Jaoyu, please, can you share your screen and start the talk when you want?
Yeah, sure. Let me share my screen. So, yeah, can you see my screen?
Yeah.
Okay, yeah. Let me interpret. So you can still see this, right?
Yeah. Mm-hmm.
Yeah, because when I present, I cannot see the the website and I cannot see the questions. So if there's any question, feel free to stop me. And so can I start or? So
Jaoyu, can you start?
Oh yeah, okay, great. Yeah, so good afternoon, everyone. And my name is Haoyu, and it's a great pleasure to be here today and to give the presentation. And so for today's presentation, my presentation topic is the smart big data in precision agriculture applications acquisition, advanced analytics, and plant physiology informed machine learning. So I think Dr. Engel, he gave some introduction of my background, and I want to briefly mention something. So I just graduated from University of California, Merced, with my PhD degree in electrical engineering and computer science. And yeah, so my research mainly focused on machine learning, artificial intelligence, and their applications in precision agriculture. And for today's presentation, here's my content. So I will mainly discuss my PhD work at UC Merced, and I will talk about a developing framework for plant physiology informed machine learning. And I will give you the definition, what is physiology informed machine learning, which is kind of adaptive to different kinds of crops and trees. And also I will discuss a set of data acquisition platforms, advanced analytics for the smart big data applications in precision agriculture. And also I will briefly introduce a non-invasive method for early detection of nematodes in walnut using the edge AI sensors. And also we will discuss some reliable tree level ET estimation methods by using the unmanned aerial vehicle system and remote sensing sensors. And if we still have time, I will give you more research I worked on, and kind of like the individual tree level water status inference, or the skill-aware pomegranate yield prediction. So that's the content of my today's presentation. So let's start. So here's the roadmap of my presentation. So there are mainly like 4 parts. I will mainly discuss the third part of my work, and for the others, I will only briefly mention them. And we have several published papers, and I will, attach some links in the presentation. So if you are interested, feel free to read more details about the papers. So in the first part, I proposed the concept of smart big data in precision agriculture. So to build the framework of the smart big data applications for precision agriculture. And I will also discuss the importance of smart big data and investigate the correlation between the smart big data and machine learning. So let's start. So the first thing I want to discuss is why big data is not smart yet. So the term big data started showing up in the early 1990s. And in this article by George Ferikin, he proposed 10 characteristics or properties of big data to prepare for both the challenges and advantages of big data initiatives. And with the development of big data technologies and high-performance computing, big data creates new opportunities for stakeholders to quantify, analyze, and better understand data-intensive processes in precision agriculture. And for the precision agriculture, in my PhD work, variability is the most important characteristic being discussed for agricultural research. And usually variability can refer to several properties of big data. And here I listed 2 things. So one is the number of inconsistencies in the data, and this need to be found by anomaly and outlier detection methods for any meaningful analytics to occur. And second, variability can also refer to diversity. So in practice, the data can be classified into several different types. For example, healthy or unhealthy, if there's water stress or any other disease. And of course, big data technology also faces challenges, which has been discussed and reviewed by many researchers. And here I listed some common challenges like big data storage and how to obtain reliable data on farm management decision-making, and both for current conditions and other scenarios of changing biophysical conditions. And which we also call like generalization. For many times, when we collect some data and we trained a model for data analysis, it may perform well in some situations. But when the environmental parameters changed, the performance will be very different. So that's something we want to solve. And some other challenges are like optimal management zones and how to extract the most useful information. And kind of inspired by these challenges, I start thinking how to make the data smart or more smart. But before answering the question, we need to discuss what is not smart. So when I talk about not smart, one is about the way I collect the data. For example, site-specific measurement, which is either time-consuming by humans or can only measure a few samples, such as the ethical variance system or lysimeter, which cannot represent the spatial distribution very well. And also currently, UAV system and hyperspectral sensors are commonly used. Another thing is too much data collection, and therefore thus reducing the data processing efficiencies. And the data set for a whole growing season sometimes is at terabyte level, but we hardly use all of them for the data analysis. And which means that although we collected lots of data, but for research, sometimes we don't use all of them, or we only use a little of them. And but our objective of data collection, our final goal of the data collection is that we collect less data or no data for related research in the future. So therefore, kind of, try to solve what is, so therefore, kind of like trying to solve the big data challenges, and I proposed the smart big data in precision agriculture. So big data technology, for example, like Internet of Things and wireless sensors enable the researchers to solve complex agricultural problems. And by applying the sensors in the field, farmers can track valuable data for farm management, such as soil moisture, wind speed, or air temperature, or humidity, and so on. And the amount of data can be huge and challenging to process timely. And therefore, how to make the big data smarter becomes necessary. So smart big data in agricultural applications can be considered as interdisciplinary research topic that is related to the extraction of meaningful information from data of plant physiology and drawing techniques from a variety of fields. For example, the UAV image processing, deep learning, pattern recognition, high performance computing, and statistics. And much hope is placed on the machine learning. And before we move on, let me briefly explain why we need machine learning. Machine learning models have been widely used in real-world applications. For example, the image processing, natural language processing, and precision agriculture. And machine learning algorithms can simplify a solution and perform better than traditional statistical approaches, which may require more hand-tuning rules. However, training machine learning models may require a large amount of data, which may not always be available for scientific problems. And then the smaller data set may cause machine learning models to lack robustness and cannot guarantee convergence. And therefore, I proposed the concept of the plant physiology informed machine learning, so which is kind of inspired by the physics informed machine learning work. And as I mentioned, machine learning algorithms have been commonly used for complex and high-dimensional problems. However, machine learning methods usually failed to extract interpretable information and knowledge from the data set. Though the training data set may be fitted well, but trained machine learning models may perform poorly for the new test data set, and leading to the generalization problems. And therefore, researchers are trying to input additional information into the training process by implementing the physical laws. Such, for example, the physics-informed machine learning may increase the evaluation accuracy, the training speed, and improve the generalization. And the definition of physics-informed machine learning was given by George in his paper, Physics-Informed Machine Learning in 2021. So in this paper, he defined the definition as the process by which prior knowledge stemming from our observational, empirical, physical, or mathematical understanding of the world can be leveraged to improve the performance of a learning algorithm. So kind of inspired that, I proposed to add the plant physiology knowledge into the machine learning training process. So when I discuss the plant physiology informed machine learning, I also focus on the variability analysis. It means that the big data can be filtered and becomes smart big data before being analyzed for insights, which leads to a more efficient decision making. Smart big data can also be defined as big data that has been cleaned, filtered, and prepared for data analysis by using the plant physiology informed machine learning algorithms. For example, when I studied the individual tree level evapotranspiration estimation, it turned out that the evapotranspiration for each tree is very close to each other. And the reason is that the mean pixel values were used for data analysis, making the ET classification challenging to implement. And considering the complexity of each tree canopy and embedding the complex information into the machine learning training process may have great potential for estimating the ET accurately. And sometimes I also call it complexity informed machine learning. Usually when the distribution of the data associated with the process of interest are based on inverse power law, the phenomenon will be complex. and complexity has been, considered as a barrier to understanding a larger variety of naturally occurring phenomena for a long time. And but still, there are some questions we need to consider. The key questions are like, how can we characterize the complexity, right? And also, what methods should be used for the analysis of complexity in order to better understand the real-world complex phenomenon, for example, such as the evapotranspiration of trees or early detection of pests, for example, the nematodes pest. So therefore, to analyze the complex information in each tree, we need to use the tail index analysis, machine learning, and big data technologies. And but before I move on, I would like to, we can move to the second part of my presentation, the smart big data acquisition platforms. So first, I would like to introduce some small unmanned aerial vehicles and remote sensing payloads. So many kinds of UAVs are used for different research purposes, and some popular UAV platforms are shown in this figure. Typically, there are two types of UAV platforms, the fixed wings and multi-rotors. So for fixed wings, usually they can fly longer with a larger payload. It usually can fly about like 2 hours, which is suitable for a large scale of field. And multi-rotors can fly about 30 minutes with payload, which is suitable for short flight missions. And for my research, I mainly used a UAV system called Hover to collect the aerial images as shown in the slide, and which is less than $1,000. And the Hover was equipped with a Pixhawk flight controller, GPS, telemetry antennas, and it can fly over the field by waypoints mode, which is designed by using the open source software, the mission planner, and the battery, has a capacity of 9,500 milliampere, which can support a 30-minute flight mission with cameras mounted on it. And one of our research philosophy is the low cost. So that's why we use a low-cost UAV system and not the commercial drones like DJI or some other commercial drones. And because for sometimes for commercial drone, we cannot integrate some new sensors because they are highly integrated. We cannot integrate new sensors. So that's why we use open source software so that we can connect any sensors we are interested. So speaking of sensors, here are some sensors I commonly used at a Mesa lab. So here I listed 4 different sensors. The first one is the let's go through them to see what they mean. So the first one is the red edge multispectral camera. So which is commonly used, which has 5 different bands: the blue, green, red, near infrared, and red edge. And for this sensor, it has a resolution of 1280 by 960 pixels, and with a 46 field of view. And the second one is a thermal camera. The thermal camera has a resolution of 640 by 480 pixels, and the spectral band is from 7 micrometer to 14 micrometer. And the dimension of the thermal camera is kind of very small. It's very light and lightweight, and the accuracy is designed to be plus minus 1 Celsius, which is commonly used for some research like water stress. The crops are very sensitive to temperature parameters. So that's why we want to use this thermal camera to analyze the water stress related research. And for some interested research topics, like because this thermal camera is an uncooled thermal camera, which means we need thermal calibration every time we use it before the flight. So therefore, that's kind of some interesting research for the thermal camera calibration. And we have a paper discussing that. So I attached at the bottom. So if you're interested in the hardwires, the sensors, you can find more details in the attached paper. So another one is a low-cost RGB camera, which is very cheap, around like $300 or $400. And it has 3 different band, blue, red, green, and near infrared. Sometimes we also can have a near infrared band. So with a spectral resolution of around 4600 by 3400. And the last one is a shortwave infrared camera. The spectral band is from like 0.9 micrometer to 1.7 micrometer. And the accuracy for the shortwave infrared camera is plus minus 1 Celsius. And the resolution is around 640 by 512 pixels. So of course, there are many other lightweight sensors. And if you're interested in this part, we have a review journal paper published in 2020, and you can find more details and discussion about the sensors in the following paper. So as I mentioned earlier, for the UAV image acquisition and processing, we prefer open source softwares. The one I commonly used is the ArduPilot, and usually the flight height was set up as 30, 60, 90, and 112 meters based on research purpose. And because there's the legal height is like 400 feet, which is 120 meters. So that's our flight limit. So we cannot fly higher than that. And the overlapping for UAV image was set up as 80%, so that the UAV imagery of the crops or trees can be stitched together during the image processing. If you use a lower overlapping value, sometimes, when there's drift for the drone, sometimes we fail to stitch the image. So that's why we prefer a higher overlapping parameters. And so here is a UAV flight demo, and for you guys might be interested in this one. So this is a demo for thermal camera flight. And you see we have a red box with ice water, and usually we use that for the thermal camera calibration. And for common procedures, usually, it's a like safety check, and we do the thermal camera warm up, which means the thermal camera calibration, and also then we take off, and then and after the drone take off, we can switch the drone to autonomous mode, and then it will fly autonomously with waypoints mode, which is controlled by our open source software, the Mission Planner. And yeah, so for time reason, I think I can skip this. So once we got all the UAV images, and we can use different softwares to stitch them into orthomosaic image. And so the software I commonly used is Agisoft Metashape. And I know that some other commercial softwares, for example, like Pix4D or QGIS, and they can also work on this. And so to minimize the shading effect on the images, the UAVs are usually flying at noon with clear sky conditions. And because each pixel in a UAV image is a percentage of the reflected light, pixel values need to be calibrated by using a known reflectance value. And therefore, the image of a calibration board needs to be taken before and after the flight missions, and servicing as the reflectance reference. So here is the common steps for the image stitching. We first align the photos, and then we build the mesh, and then build the orthomosaic. And yeah. So once we process all the images, we can get, for different research purpose, we have different orthomosaic image. Here I listed 4 different images, UAV stitched image. So the first one is a near infrared image for the pomegranate field. And the second one is an RGB image for cotton field. And you see that in this area, you can see some soil. And so that based on sometimes when we see this area, we have you can see the soil. So for some research purpose like water stress, and you can use the RGB image to detect where there's water stress. And the third one is a RGB image for tree canopy. And for some research, we are interested in the tree canopy segmentation. So that's why we use the high resolution image so that, for example, we can do the tree canopy segmentation, which means we can detect each tree canopy individually. And the last one is thermal. The thermal image for the pomegranate field, like I mentioned earlier. So if we have some, for example, if we have some water stress research, and we can use thermal image for our research. So is there any questions so far? So I can't see the chat window, so I'm not sure if there's any question. So if not, I will move. If not, I will move on. So of course there are many. Of course, for flying a UAV system, there are many challenges and opportunities. And for example, the hardwires itself, and I know many research teams, they're working on using the different robotic system to control the UAV system. For example, like the one of the research topic I worked at Cornell is to use the ROS system to fly the drone autonomously. And ROS means the robotic operation system. And sometimes, because sometimes you don't want to, manually fly and take off the drone. So that's why we want to have a robotic operation system, to control the drone. And also like for software issues like the UAV path planning and image processing can be also some challenges. And also, as I mentioned earlier, the camera calibration can also have some challenges, and also like the image stitching and also mosaic image generation. So sometimes we can have some different research issues, and that can, push us to think of new research ideas to solve those problems. So let me give a case study first, and how we can use the UAV system and all the things machine learning, and how we can use that for the research. So this research is a UAV resolution and waveband aware path planning for the onion irrigation treatment inference. And there are 3 different irrigation treatments, and we want to use the UAV image to detect and classify the irrigation treatments. So why onions? Because onions is widely used in different countries and cultures during all seasons in a year. And California produces the most onions in the United States. And in 2018, it produced around 1/3 of the total onion crops in America. And on the other hand, experiments showed that in any growing stages, water stress can cause reduction in onions yield. And so therefore, to optimize the irrigation schedule, it's necessary to have accurate and reliable water stress monitoring methods. So, study said, so the flight mission was designed. The flight mission design was tested in an onion field at USDA during the growing season in 2017. And since 2016, an onion test field has been set up for research of biomass, soil amendments, and deficit irrigation. So there are 3 different irrigation treatments, and there are 3 replicated plots for each treatment combination. So here is how the onion field looks like in our UAV RGB image. And you can see that we have different blocks in this onion field. And here's the most straightforward table. And for each onion, there is a plant ID number, and there are different irrigations and biochar treatments. And our final goal is to differentiate all combinations of the onions. But to use machine learning algorithm to train the data, we need lots of samplings. And but usually there's a limited data set. So for this one, we only focus on the irrigation part. So here is the treatment images. You see that there are 36 plots in total, and each plot has 40 inches wide, by 20 meters long. And we use 3 different colors for irrigation treatments. The green means the high irrigation, and the black means the medium irrigation, and the purple means the low irrigation. And so our goal is to use machine learning to classify the different irrigation levels. So therefore, that can give better decision makings for the stakeholders and farmers to like how much water they should irrigate and how to compare the water stress. So to prepare the multispectral and thermal images dataset, we first segment the 36 plots from the whole onion field. And in order to focus only on the area of interest as shown in the slide, so every image can be converted into a 2048 dimensions vector for data processing, either by Python, MATLAB, or any tools you feel comfortable. And data was distributed as 67% for training and 33% for testing. And several classifiers are being used for the onions irrigation treatment inference. Here are some classifiers I listed: the nearest neighbors, the linear support vector machines, and which is the common, so the tool is by the scikit-learn machine learning algorithms. And from the table, you can figure out that the best accuracy is around 70%, which shows up when the resolution is at 2.02 centimeters per pixel by using the neural net classifiers, and which is about 60 meters above the ground level. So compared with the other classifiers, and the neural net classifier performs the best in all resolution levels. It turns out that when we fly a drone in the field, higher resolution does not mean a better analysis results. So this makes us consider if there's an optimal flight height for data analysis. So we don't have to fly lower, and sometimes flying lower means you may consume more energy and may need more time for your research purpose. And so for this slide is a resolutions effect on data analysis, and we are trying to compare the different flight height for the data analysis, and we use entropy as the quantitative analysis and evaluation of the image information. And you see that because the energy provided better comparison of the image details, so you see that when we fly the UAV at different height, there's no consistent results from the table. So that means when you fly a drone for your research, make sure the most important thing is to keep your flight altitude consistent. So another one is about the waveband configurations, remote sensing images. So there are red, green, blue, and near infrared and thermal band. So as shown in the table, there are 4 different combinations, and we use the RGB combined with the near infrared. We have the RGB, near infrared, and thermal. We have the thermal only, and we also add so for the all means we combine all of them, and we also add a vegetation index. And from the table, you can see that the best accuracy is around 84, which appears when the RGB, near infrared, and thermal band were used by the Gaussian process. And based on the accuracy of the Gaussian process, it is meaningful to point out that the thermal image itself can already get pretty good estimation results, as high as around 80%. So that means we do not always need multispectral wavebands information for some coarse estimation research work. So here I attached the paper here. So if you are interested in this research work, you can find more details in this paper. So that's the second part about my presentation, the UAV and remote sensing payloads. And I also discussed some also give a case study. So next, I would like to talk about the third part of my research work. So in chapter 6, I will give a non-invasive approximation sensing method for early detection of nematodes. And let's say, so that's the third part, the advanced big data analytics, plant physiology informed machine learning, and fractional order thinking. So one of my research area is the pest management, and which means so from one of my project is a low-cost proximal sensing method for early detection of nematodes in the walnut using machine learning algorithms. So nematodes are microscopic eel-like roundworms, and the most troublesome species in the garden are those that live and feed on the plant roots. So as shown in the image, they can steal the nutrition water from the plant, and they have a huge impact on plant health and crop yield. Although in California, there are many different species of root-feeding nematodes. The most damaging ones to gardens are the root knot nematodes. And the root knot nematodes can attack a wide range of plants. In our research, I only focused on the walnut. So for the study set, it was conducted in an experimental walnut orchard at the Kearney Agricultural Research and Extension Center. And there were 3 different replications, and which is the project 30, project Smith, and project 45. And so to measure the nematodes numbers, traditional methods can be time-consuming and tedious, and I will quickly go through this part. So you see that if we want to find out the nematodes number, so the first step is, we need to dig into the soil and find the walnut roots. And then we collect all root samplings, we'll put in a cooler with a label. And after we go back to the lab, we have to clean the walnut roots and cut the root into pieces. And we usually, pick 20 grams of our sampling. And then we flush the roots for a few days, in order to save the nematodes at the bottom of the tube. And at the end, we go to the lab and we use microscope, to manually count the nematode numbers. And in the last image, you can see this is how the nematode looks like. So you see, this is kind of, tedious extraction procedures, and usually it can take several weeks, up to a few months, to count all the nematodes in order to get the ground truth. So that's why we want to figure out if we can find some features, correlated to the nematode numbers. So therefore, we don't need to count the nematode numbers manually all the time. So that's the measurement signal of. So that's why we use a sensor called Wallabout for the radio frequency measurement. And the measurement signal of the radio frequencies reflectance of the walnut leaves using Wallabout. And our research hypothesis is that the reflectance of the walnut leaves will be significantly different towards the root lesion nematode infection levels. So the spectral curve obtained from the leaves of walnut trees infected with nematodes could show the characteristic pattern of walnut under the nematode stress. And usually we, for the sensors, is connected to a host device. This can be our computer or some other device. And how it works is that it will emit the radio frequency signal, and then we measure the reflectance from the walnut leaves. And this is how the sampling looks like for our radio frequency measurement. And this is a sampling from one walnut leaf. And then we can use, for example, we can convert this signal into a vector, and we can use machine learning, to extract the most useful features and do the classification so that we can detect the different nematode infection levels. So that's the research for this part of the work. And for example, for the project 45 in 2019, there were 15 sampling trees from 6 different blocks. And based on the ground truth and the nematode numbers, I manually classified them into 4 different nematode infection levels. And then I used the linear discriminant analysis method, for the data visualization, and which learned the most critical axes between the classes. And the axes were then used to define the hyperplane to project the high-dimensional training data into two dimensions, and which gained important insight by visually detecting the patterns. And in the image, the x-axis and y-axis had no scale because of the hyperplane projection. And the nematode infection levels were successfully clustered into 4 levels, and the color bar values represented the 4 different nematode infection levels from 1 to 4, and which means from low to high. And here are some research results of this part. And you see that the nearest neighbors gave us the best, gave us the highest accuracy, which is 95%. And the table showed the details of the test process of the k nearest neighbors method, which was a type of instance-based learning that did not attempt to construct a general internal model, but simply stored the instances of the nematode infection levels training data. And for the other classifiers, test performance and the accuracy of the support vector machine was around 57, and for the others, and I'm not going to go through this for details. And so we have a paper attached here. So if you're interested in the pest management work, you can find more in this paper. And we use a confusion matrix as a prediction result, as the summary of the prediction result on the classification problem. And the number of correct and incorrect predictions were tallied with the count values and divided into classes. And the confusion matrix provides an insight not only into the errors being made by a classifier, but more importantly, the types of errors that were being made. And the true label means the ground truth of the nematode infection levels, and the prediction label identified the nematode infection levels predicted by the trained model. And you see that for the nearest neighbors, it has the correct, so this is the correct predictions on this diagonal. And we also have similar work on 2020, and we did this in multiple years because we want to make sure the trained model is robust for different situations and for different weather situations. So that's why usually we need to do this for multiple years. So I'm not gonna go through the details here. And for this part of work, the conclusion is that we have, the trees severely infected by the nematodes. They show the different radio frequency reflectance, and similar to the plant response to the other environmental stress. For example, such as the drought, the nutrient deficiency, the salinity, and the biotic stresses. And furthermore, the findings of this research provided insights for the early detection of nematodes using phenotyping and machine learning technology. And also, the study was limited by the lack of information on the biophysical explanation of what variations of the walnut leaves were responsive or sensitive to the radio frequency signal under the pressure of nematode. So that's kind of the part for this research. So is there any question for now? If not, I will move on to the next part. So another research I mainly worked on is the evapotranspiration estimation with the small UAVs. So evapotranspiration also is called the ET, is known as the mean outgoing water flux from the surface on the Earth. So ET is a combination of two separate processes, the evaporation and the transpiration. So mapping the ET temporally and spatially can be useful for many agricultural applications. For example, the soil moisture monitoring, assessing the crop water stress, and weather forecast. And usually we can use satellite images, but there are some limitations for satellite image. For example, sometimes the resolutions are kind of low, and the Landsat thermal, the resolution is like 90 meters per pixel. And also the revisit cycles, for the Landsat is like 17 days, and for the Sentinel-2, the revisit cycle is just like 1 to 2 days. And to get better spatial and temporal analysis of the ET, that's why we prefer by using a UAV system, which kind of provide us a higher resolution, and we can fly the drone and at any time as long as the weather condition is good. And many researchers have been using the UAVs for ET estimation. And for example, as I mentioned earlier, we have a review paper published in 2020, which we discussed the researchers' work at the ET estimation. And for our research work, it's also conducted at the USDA in the Palier, California. And it's a pomegranate field, which was planted in 2010 with a 5-meter spacing between rows and 2.75 meter within row tree spacing in a 1.3 hectare field. And for the ground truth is a lysimeter site. So this is how a lysimeter looks like. And usually the lysimeter have a resolution of approximately 0.1 millimeter of water loss. And you see that it can record the data every hour. And you may wonder why we don't use lysimeter, why we don't just use lysimeter, right? Because lysimeter is kind of very expensive. Like for this one, it's kind of like millions of dollars, and which is impossible, to commercialize it, right? And this, you see that there's only 2 trees planted in the lysimeter. So that's why we are trying to find a low-cost method so we can analyze the ET spatially and temporally for the whole field. And you see that this pomegranate field was randomly designed into 16 eco blocks with 4 applications to test the 4 irrigation levels. And the irrigation volumes are like 30, you see that here we have different irrigation volumes, which are 35%, 50%, 70%, 75%, and 100% of ET, which was measured by the weighing lysimeter in the field. And for the features we used is the normalized difference vegetation index, which has been commonly used for vegetable monitoring, such as water stress, crop yield, or ET estimation. So the NDVI is calculated by the near infrared and the red reflectance. And it's a standardized method to measure the healthy vegetation. And when the NDVI is high, it indicates the vegetation has a higher level of photosynthesis. And so another thing is that we use the crop coefficient method. So the crop ET is determined by the crop coefficient approach, whereby the effect of the various weather conditions are incorporated into the reference ET, and the crop characteristics into the crop coefficient. And the objective of this study was to investigate the approaches of estimating the crop coefficient using the UAV-based NDVI. And then we can use the crop coefficient to estimate the actual ET. And for the reference ET, we can get this value from the weather station, and we can estimate the crop coefficient by the UAV image, and so that we can estimate the actual ET. And you see that the values of crop coefficient were derived using the equation, and the crop coefficient was recorded by the weighing lysimeter in the center of the pomegranate, and the reference ET is recorded by the weather station near the pomegranate field. And you see that the maximum values of crop coefficient and NDVI is at the mid of the growing season, and after the peak of the mid-season, the crop coefficient, started decreasing. Both of them are kind of like very low. That's because most leaves fell off the pomegranate trees after the harvest. Therefore, this data was not used for the further data analysis. And you can see there's a strong correlation between the crop coefficient and NDVI during the growing season in 2019. So we can use the NDVI to estimate the crop coefficient. And so for time reason, I will go a little bit, I can skip this one, So once we got the data set, we will use a neural network called the Deep Stochastic Configuration Networks to find the correlation between the crop coefficient and the NDVI. So here are some results for our trained model. And once we got the crop coefficient, we can analyze the spatial variability of the ET for the whole field. And so you can see you can figure out the spatial variability of the ET. And here are some similar works, which is the tree level ET estimation. And so similarly, we generate the crop coefficient, and we can get the crop coefficient mapping of the whole field. And once we got the crop coefficient, we have the reference ET. By times them together, we can get the actual ET. And so this is another result to show you how the individual tree level ET estimation how they change during the whole growing season. And there's a box plot of it. So for the ET estimation part, we can conclude that the UAV flight missions were conducted to collect high-resolution multispectral imagery in a pomegranate orchard at USDA. And the experimental results showed that the estimated daily ET has a very high R-square, and which it means is a very robust method to estimate the ET. And in the future, for this part of research, there are 5 requirements for mapping ET with high fidelity in the future, which is high frequency, high spatial resolution, high temporal resolution, and large spatial coverage, and long-term monitoring. So that's the part of the ET research work. And I was told the presentation was like 45 minutes, so I think I'm already spent 5 more minutes, so I'm not sure if I should stop here or.
How are you? Thank you very much with your conference.
Yeah. So I will stop
it's
here.
It's very interesting.
Yeah. Because Cairo told me it's the 45 minutes presentation, right?
Okay.
Yeah. I have more to show, but I guess
okay.
I'm running out of my time.
Okay. Next we look at the question with help of Jairo. Jairo? Hola, Jairo.
Yeah.
Hey, Jairo is here.
Hola, profe.
There are questions?
Okay. Yeah, there are some questions.
Okay.
The comment section.
Yeah.
Um,
Oh, yeah, I do see some
here
questions.
that we have the first one here. Uh, is it better to have um, a smaller processing time with low resolution images, or big resolution images with low inference times, knowing that the precision, considering that the precision is similar in both cases?
The connection. I didn't hear your question. There was some, I think I lost the connection. Yeah.
Can you hear me?
Oh, yeah. Now I can hear you. So can you repeat your
Maybe
question?
can, yeah. Um, there is a question here that says, is it better to have um, smaller processing times with low resolution images, or high resolution images with high processing times, considering that the precision is similar in both cases?
Oh, so you're asking about the processing time for low resolution and high resolution, right? Is that the question?
Yeah, which is preferred? Low resolution image with faster processing time, or
Mhm.
high image with with higher processing time?
Yeah, sure. Of course. And so I think for the UAV image, that's not a concern for the research. The thermal, for example, the thermal camera, we may have the resolution which is like 8 centimeters per pixel. And for the multispectral camera or the survey 2 camera, the resolution might be higher, which is 1 or 2 centimeters per pixel. And usually that's fine. When you process your images, we usually don't change that. We don't need to change any settings for processing the image. Of course, that if you use lower resolution, that will be fast. Of course, that will be faster, right? But that's not an issue for when we're processing the UAV image for the agricultural research. And also, the only situation that you need to consider the resolution issue is when you do the data fusion. And for example, when you want to combine when you want to do the image registration for a multispectral camera and the thermal camera, because they have different resolution. In that case, you may consider you may need to consider the image registration technique and to realize the data fusion. And that's sometimes when we consider the image resolutions, but usually that's not an issue for the processing time. Yeah.
Um, there is another question here. Uh, Here says, excellent presentation. I would like to know if the application you show, which is in a commercialized stage, what type of funding you get to do this research?
Um, yeah. So thanks for your question. And so for the foundings, usually when we were like PhD students, we were trained to write proposals and for different, funding sources. Like for example, like the NSF or NIFA or Bayer Crop Science. There is a big agriculture research company called Bayer Crop Science. I also won a proposal from that, and also for some other funding resources, we are always, we apply we write proposals almost every year. And currently, because now I'm not a PI, I'm not the principal investigator, so usually I don't need to consider the funding source issue by myself. And I mean, even for postdoc, because as working as a postdoc, it's kind of more independent research, but the funding comes from your PI. And of course, that every year we will write proposals together, and but usually the funding is coming from like some companies or some like the NSF or USDA, and to get some common funding resources. And for commercialization, I think of course we are interested to do the commercialization. For example, in some companies in the Bay Area, like Drone Deploy, and also the Bayer Crop Science, or some other academic institutes like Texas A&M or the Cornell University, and we are trying to commercialize that. But for agriculture research, collecting data is not easy, and there are lots of things we need to consider about. But we do focus on research first, for commercialization. And I think companies spend more time on how to commercialize. But for research institute, for the college, for the university, and we care more about the most innovative methods to do research, and for commercialization, we may not, care too much about that.
All right. So there is another question here.
Oh.
Excellent presentation. My question is if the commercial use of the project is limited to a specific region or doesn't have any restrictions for its use and commercialization in different countries.
Is it the same question or is it a different question?
It's a different question. Basically, if the project has some restrictions to be some exportation controls to be applied in any other country.
I don't think so. I don't think there's a limitation for the research, and because it's not patterned, and so I don't say there's any limitation to apply this to the other countries or the companies. And
question here. Have you correlated soil properties with the image taken from the crops? What kind of results have you analyzed on this topic?
Soil properties with thanks for your question. So for this research and the soil, so for example, for the pomegranate, for the onions, the soil is uniform. I mean, for the pomegranate, it's uniform. So we didn't compare the different soil types, but that would be a very interesting research topic. For example, we can set up different plots, and we can use different soils and to compare the results. So yeah, but for my research, I didn't consider the soil properties because for that pomegranate field, it uses the same soils. Yeah, there's no difference between the soils. Yeah.
Okay. Any other question?
Yeah, I can see some comments. Yeah, I wish I know Spanish.
Okay. Okay, how are you? Thank you so much.
Yeah, no problem. Yeah.
We look forward your participation in future events.
Yeah, thank you. Yeah, thank you so much.
Thank you, how are you?
For joining the meeting.
Okay, thank you, how are you? Para finalizar, quiero agradecer al doctor Jairo su participación y a Claudia Jimena y a Javier de la Oficina de Comunicaciones y Relaciones Públicas de la UPB el apoyo brindado para la organización de este evento. De igual forma, quiero agradecer a todas las personas, profesores, estudiantes y demás interesados que han participado en esta charla a través del canal YouTube Live de la UPB. Su participación es muy importante y esto nos anima a seguir realizando actividades académicas de este tipo. Nos veremos en otra oportunidad. Una feliz tarde para todos. See you later. How are you?
Yeah, see you. Thank you, everyone.
Bye, how are you?